Good morning and happy Friday. We're so glad you are here this morning. My name is Phyllis Newbill. I'm an Associate Director of Youth and Community Education in one of several different centers within ICAT. We are here for the ICAT Playdate, the Institute for Creativity, Arts, and Technology. A few housekeeping things before we get started this morning. One is that there is a recording of this happening right now. We are live streaming. Good morning if you're watching us online. We're glad you're here as well. So just know that you're being recorded. There's a clipboard that will go around in just a minute. Please be sure to sign in on that. A couple of things happen with the clipboard, but most importantly, that is how we justify donuts and coffee, which is a very important part of an ICAT Playdate. Please enjoy donuts and coffee. When you have questions, just wait for me to get to you with the microphone so that our friends online can hear you, even if you have a fabulous voice. And if you're online, I hope you'll use that questions link and send us a question. We'll read it here and share it with our presenters. If PDN or Professional Development Network credit is helpful to you as a Virginia Tech faculty member, please just, you'll need to register for that and let me know if you have questions about that. And make sure you check in with me to give you credit. We have lots of things coming up in the next few weeks. It is, welcome to April in Academia. First thing is there's an art exhibit right behind us, actually. There's a student art exhibit happening, and I'm pretty sure that at least one piece is painted by someone in this room or who usually comes to Playdate. There's Damon. I just looked right over your head. Anyway, so Damon's got a piece in it, and anyway, make sure you check that out. Also, tonight in the Cube at 6 o'clock is a beat battle. On Monday from 12 to 5 in the Cube is Learning Landscapes. And next Friday, a week from today, 8:30 p.m., is Indigenous Mixtape. So these are all really amazing projects, and you should check them out in the Cube. Today, Connor Dunlop is with us, and we're learning about plant ecosystems and AI, and I am fascinated and can't wait to hear what you have to say. Thanks, Connor, for being here.
Hi everyone, my name is Connor, and I'm a current PhD student here at Virginia Tech studying computer science. My main research interests lie in generative AI and interpretability within AI. And today I want to talk about our project Verdant Visions, visualizing plant ecosystem change through generative AI. Verdant Visions is a project at the intersection of art, artificial intelligence, and environmental science. Its core mission is to visualize how climate variables like temperature, rainfall, and carbon levels affect plant ecosystems. Using AI, the project generates dynamic, evolving artworks that reflect environmental changes as a result of changes in climate. And by making the effects of climate change visually and emotionally tangible, Verdant Visions invites viewers to not just understand, but to feel engaged in environmental shifts. Ultimately, the goal is to foster greater public engagement and raise awareness about climate issues in a way that's accessible, compelling, and impactful. Before talking about our project, let me go into some background on AI image generation. So over the past decade, image generation has seen remarkable advancements. Early models like GANs, generative adversarial networks, laid the foundation, steadily improving in their ability to produce realistic images. However, a major leap forward came with the introduction of diffusion models just a few years ago. These models revolutionized the field by enabling the generation of stunningly detailed images from simple text prompts like, for example, a robot hokey bird from Virginia Tech, bringing creative concepts to life with unprecedented fidelity. So, diffusion models are a core architecture behind many of today's leading generative AI systems. The idea is to start with clean training data, like an image, and progressively add Gaussian noise or noise sampled from a normal distribution over many steps until the data becomes indistinguishable from pure noise, as shown on the left. Then the model is trained to reverse this process, learning how to denoise step by step until it reconstructs the original image, shown on the right. This technique enables the model to generate entirely new data by starting from random noise and applying the learned denoising process. So here's a closer look at how diffusion models actually work under the hood. The process starts with a real image, shown here as x0, and gradually turns it into noise over many steps, normally around 1,000 steps. And each step adds a little more noise, and this sequence of steps is modeled as a Markov chain. And a Markov chain is just a fancy way of saying that each step in the process strictly depends on the step before it. And eventually, by the final step, xt, the image is completely unrecognizable, and it's just pure Gaussian noise. This gradual noising process helps the model learn how to do the reverse, starting from noise and working backwards to generate a new realistic image. So essentially, the model learns to understand data by first destroying it in a controlled way and figuring out how to put it back together. As mentioned, in a diffusion model, the training objective is to learn the reverse of a predefined noising process. Given a noisy input at some time step, the model predicts the noise that was added at that given time step. And by accurately estimating this noise, we can subtract it out and recover a slightly cleaner version of the data. We repeat this over and over again, and this reverse process is what enables diffusion models to create new data from scratch. Now I'll continue by going into some related work. To begin, I'd like to share some of my previous work that directly inspired this ICAT project, CREA. In that research, our primary goal was to transform everyday images into imaginative and creatively reinterpreted visuals. For example, if a user provides an input image, such as a simple white dress or a basic teapot, our method can reimagine and transform that object into something far more artistic and unique. The system isn't just limited to single images either. It can also generate entire sequences, producing creative visuals or videos that build upon and reinterpret the original input in novel ways. This exploration of creative transformation laid the groundwork for our current ICAT project, where we push the boundaries of generative AI to spark new forms of visual expression. So before getting more into details about the CREA methodology, I want to talk about some motivation on why our proposed framework is necessary. Creativity in generative AI remains a core challenge, especially in visual domains. While current models can generate visually impressive content, creativity demands more than just simple high-quality visuals. It involves producing outputs that are novel, expressive, and artistically rich. Current workflows rely a lot on the user, and this often requires manual adjustments to the generation prompt, manual edits to images, and precise adjustments to model parameters. And this can make the entire creative process very time-consuming and tedious for users, putting the burden on the user rather than on the model or system itself. So how can we fix this? We argue that we need to go beyond the one-shot prompt-to-image paradigm, and instead we need frameworks that can reason, iterate, and refine creative outputs just like humans do throughout the creative process. To address the limitations of current prompt-to-image pipelines, we introduced CREA. CREA is a multi-agent AI framework designed to emulate how humans approach creativity using autonomous collaborative agents. Instead of relying on a single model output, CREA structures the generation process as a dialogue between specialized AI agents, each with a role inspired by real-world creative teams. For example, our framework introduces specialized AI agents like a creative director to set the overall creative vision, a prompt architect to formulate imaginative prompts, or a generative executor to generate or edit a creative image. And these AI agents don't work in isolation. They actively communicate and refine outputs across multiple iterations, allowing CREA to develop novel and diverse creative ideas. So here's a diagram outlining our entire approach for this method. We'd divide our framework into 4 main components: pre-generation planning, creative image generation or editing, post-generation evaluation, and self-enhancement. So let me talk about the first phase, pre-generation planning. During this phase of our framework, 3 AI agents work together to produce an initial high creativity prompt: the creative director, the prompt architect, and the generative executor. First, the user provides an initial image to edit or a concept to generate, like a couch. Then the creative director creates an initial creative blueprint for all the other agents to follow. And given this creative blueprint, the prompt architect generates a high creativity prompt using a two-step process. First, the prompt architect generates 6 initial contrasting prompts, and these prompts are all grounded on like actual definitions from creativity theory. For example, we generate prompts for creative principles like originality, expressiveness, interpretability, and depth. And next, the prompt architect synthesizes these diverse prompts into a single fused prompt suitable for generation or editing. And throughout this entire process, the creative director, prompt architect, and generative executor all collaborate to like ensure the final prompt is suitable for generation or editing or whatever task we're doing. And given this finalized prompt, we enter into the second stage of our framework, creative image generation or editing. During this stage, the generative executor decides whether we should be doing creative image generation, editing, or any other task that you want to plug into this framework. And once it makes a decision, it calls the appropriate model to do either editing or generation, or whatever other task. And once we have a generated or edited image, we evaluate this image using another agent we call the art critic. This agent uses a multimodal large language model to score the image with a score between 0 and 30. And we base this score off the same creativity principles that I mentioned before. And finally, given this creativity score, we can either finalize the generation or edit if the score is sufficient, or continue on to the final step, self-enhancement. And during self-enhancement, we introduce the final agent, the refinement specialist. And this refinement specialist generates a structured refinement plan based on the feedback from the art critic. And given the refinement plan, the prompt architect is asked to refine the previous generation prompt. Afterwards, we repeat the entire process over again to iteratively refine the outputs to increase overall creativity. And we repeat this process until either the creativity score is sufficiently high or we exceed a set number of iterations. And throughout the entire process, agents collaborate and give feedback to each other to ensure everything stays aligned and has the same goal of producing only the most creative outputs. So here I show some results from our framework for image generation. Given just a simple user concept like a couch, our framework can produce both highly creative and diverse generations. Here's some results produced by our framework for creative image editing. Given an input image, our framework is able to produce results that are not only highly creative, but that also preserve the structure of the original user input image. And lastly, here are some results demonstrating the versatility of our framework by extending our work to video generation. Given the initial concept, Cray can generate and refine complex video scenes with minimal user input. So now I'll talk about the main project for today, Verdant Visions. In this project, we explored how diffusion models can be applied beyond just generic image generation, specifically for visualizing the effect of climate change. Our goal was to create images and videos that not only depict environmental transformations, but also make these changes more tangible and emotionally impactful. The example here shows a side-by-side comparison of a healthy cornfield and one that's been severely affected by climate-induced environmental stressors. To create these kinds of visualizations, we use text-to-image diffusion models. These kinds of transformations help visualize how environmental stressors might alter plant ecosystems over time. By using diffusion models in this context, we're able to simulate complex environmental changes in a way that's more concrete and accessible to the public. We start with simple prompts like a healthy cornfield to generate baseline scenes, then we can modify those scenes to reflect climate-induced changes like dry soil or withered crops. Here's a closer look at our generation pipeline. We start with a text prompt, such as a healthy cornfield, and pass it into a text-to-image diffusion model to generate an initial image. And given this initial image, we ask a multimodal large language model to provide details on what would change in the initial image, given the effects of environmental stressors. And from there, we can leverage existing image editing techniques to modify the scene, simulating how it might look under climate stress like drought or extreme heat. And to make our visuals more immersive and dynamic, we extend our approach from static image generation to video generation. Given a before and after image generated using our pipeline, we can use video diffusion models to animate these scenes. Here we show some before and after images initially generated using diffusion models. And here we show their animated counterparts, which we create using video diffusion models, making these scenes more visually interactive and engaging. Okay. In the final stage of our pipeline, we interpolate between two generated video sequences, typically representing a before and after state, such as a healthy environment and one affected by climate stressors. This interpolation enables us to produce a smooth, continuous transition between the two states, resulting in a single cohesive video. And while our primary focus was on plant ecosystems, the method can be applied to other types of scenes as well. It can be applied to visualize a wide range of climate impacts beyond vegetation, such as flooding, severe weather, and wildfires. Looking ahead, our objective is to evolve this project into a more interactive and adaptive platform. Specifically, we aim to connect the system to real-time climate data, allowing it to dynamically update visual outputs in response to current environmental conditions. This would involve integrating live inputs such as temperature, precipitation, and seasonal shifts so that the generated images and videos accurately reflect ongoing changes in the climate. The long-term vision is to create a system that doesn't just simulate climate scenarios, but one that can visually track and respond to climate change as it unfolds in the real world. So that's all I have for today. Thanks for listening, everybody, and if anybody has any questions, feel free to ask.
Thank you. What questions do we have?
It's really brilliant. So I'm wondering, is this basically developing an AI model, or is it really about climate education? And if it's the latter, could a user adjust parameters like changing the temperature, changing water amounts, things like that?
For sure, that's the goal. We mainly the main goal is to use this as an educational tool for people to better understand the actual impacts of climate effects. It would be, yeah.
Hi. Are you training any part of this to, I don't know, look at specific? I mean, you're looking at plant ecosystems specifically. That is a very, very, very broad thing. Mm-hmm. And in my experience, using generative AI to do anything with plants, you end up with very generic sorts of plants, or the plants that are very well known. Like it'll do corn well because there's probably infinite images of corn out there in the world. But plants respond differently to different plants respond differently to climate change, right? And different sort of climate areas in the world. So I'm wondering about training it specifically to show how that would happen and how things change. Climate change doesn't mean everything's going to be dry and dead, yeah, right? It just means that this might turn into a tropical jungle. So I'm wondering if you all are thinking about that. I know that might be a next step for this because this is a beginning, but I'd be interested to hear what you have to think about that.
Yeah, and I think you're 100% correct in that. A lot of these models have inherent biases. As you mentioned, it tends to visualize climate change as dried out and stuff like that. Definitely something we have considered is using additional training examples to guide for other scenarios as well. It's very expensive, which is why a lot of times people often try to avoid training and use just off-the-shelf approaches. But yeah, you're 100% right in that because of the biases within these models, we definitely need to consider that as well.
How are you thinking about balancing using these tools for climate change education when they also contribute to climate change?
Can you repeat that, actually?
Sorry, I do have an accent. I can slow down. So these are tools being used for climate change education. Mm-hmm. How are you thinking about the balance of that work with the impact that tools like this have on climate change?
Balance that work. Yeah, I mean, like, I guess, like, sorry, I'm misunderstanding the question. Like, what is the balance between?
I'll try it. So the AI computers themselves are
Yeah, yeah.
contributing to climate change. How are you?
Oh,
How
yeah,
are you
I
go-
guess
yeah.
I understand. I understand. Yeah, that's definitely a consideration. I mean, I guess, like, we haven't really considered that because you're right, like, these systems are definitely, like, a main contributor to climate change, like OpenAI, like, I mean, opening massive data centers using so much, like, energy and stuff. But I think by leveraging the tools that are going to exist anyway, we can help bring more awareness to this topic.
So this is not a question. This is actually introduce myself. I'm Song Li. I'm the associate professor in the School of Plant Environmental Sciences, and I'm a co-PI of this project. So the next step will be naturally to connect this really awesome AI model with scientific knowledge of how realistically climate change will affect plant growth, and make it a really good education tool, let people be more aware of the effect. And for example, we were thinking about taking a picture of, for kids to take a picture of your field, and then say, 20 years from now, when the temperature rises another 2 degrees, what will happen to the field? And so those type of things. But also, we need to be a little bit aware of the current climate, or political climate, how this type of thing can be funded down the road. So that's another issue. But that's what we want to do, scientifically inform the generative AI, so to provide scientific knowledge-backed AI generation.
Okay. Hi, I'm Pınar Yanardağ. I'm advisor of Kanır, and I work with Song Li, and I'm from Computer Science Department. So something to mention about these models contributing to also like impact in climate change. The models that we are using are pre-trained models released by these large companies. So those models, they cost about $10 million to train, and they definitely consume a lot of, like energy, and they actually damage the environment. But this is a big consideration in our research. And we only use pre-trained models, and our models are very efficient, like uses a couple of minutes of GPU time. So hopefully we are not contributing in this project, but that's definitely a big concern. Yeah, thank you.
So unintended pun, of plant growth is soil, water, and light. One question, I'm wondering if you're integrating soil, like this area has a heavy clay soil, which affects obviously permeability, so you tend to often have plants that are drowned at the root level because the water doesn't go anywhere. So you're integrating soil, and have you thought of working with extension, or there's so much agriculture in Virginia that extension might be a source of funding, especially if it's education related, because you could have from farmers down to school kids interested in the information that you're generating from this.
Something to consider. I mean, incorporating that type of real data can definitely help improve this framework for future work.
There's one online. This one's coming in from online. Sorry, there's several. Have you learned anything about the nature of human creativity by trying to create an algorithm that simulates it? Thanks, Carl.
Yeah, I mean, I think so. I mean, like, if we're talking about the Crea work as from earlier, like, especially like when you dive into like some of that creativity theory and like actually try and ground the AI and like this sort of knowledge, it kind of like it's a good way to show like the creative process.
Sorry, this is a long one. The Harvard Business Review, I think this is just, there is a question, okay. The Harvard Business Review states that the global AI energy demand projected to exponentially increase to at least 10 times the current level and exceed annual electricity consumption of a small country like Belgium. A statistic worth noting is using AI tools to address climate change rather circular, so it's a similar question to before, given this drastic increase in electricity consumption, and particularly given that the current administration maybe, is unlikely to fill this demand with clean sources of energy. So, sorry, that may have come in earlier and I'm not
Yeah, I think
matching.
that's been answered.
Yeah. Other questions?
Yes.
I was just, and again, it goes back to the creativity, and I'm just trying to understand, because I really was interested in that creativity model that you had at the beginning, and how does that influence the I couldn't, and it's my fault, but I couldn't make that connection between the methodology that you showed there, that methodology, and then how that impacted the visualization of climate change in the second part. Well, and you said
just this let me see. So just this type of transformation of image editing and using multiple different pre-trained models, editing models and LLMs in working together to create the final output.
okay. I'm curious whether you just did kind of an A/B type of approach just to see, because as was asked earlier, right now it looks, and you even said there's sort of this bias right now in visualizing, what happens with climate change, et cetera. And I was wondering, do you're using this technique, does that in any way influence or pull it away from the bias more towards something? And I'm just curious how this connects to one to the other.
Yeah, it definitely could mitigate the bias. I mean, incorporating more of this collaboration between different models allows them to be work more powerfully, essentially. I mean, I don't know if that answers your question, but Dr. Yonardog has something to say too.
Actually, this work gave us a lot of insights about how we can build a system where, for example, one agent can connect to climate, like sensors. One agent could be connected to, determining what kind of climate change impact based on the location are expected in this, for this particular image and then transforming. So that's what we are focusing right now. We want to connect this framework to, real indicators. And then the way that we are working on is we want to create these specialized agents. And then the whole framework will be these agents coordinating with each other and then creating this final, visualization which accurately shows how this location or the, particular area that you are trying to estimate, the impact will be accurately reflected. Yeah.
Thank you. I just have a quick question, I think, or let me, I'll do James's. His is better.
Yeah, so I was just wondering, have you tried to isolate individual variables? Because I'm imagining that if you wanted to do a tool that sort of takes climate factors into consideration, like specific scientific climate factors, then you'd need to be able to say I need the soil, I don't know that much terminology, but I need the soil to have this level of moisture or something. Have you tried to isolate those individual variables and then generate images that specifically only target one variable, basically?
Yeah, we've tried that, and it is capable of doing that, but we also want to plug our framework into real data to actually more accurately reflect what the scene would actually look like based on real data.
And can you talk, just to close us out, can you talk briefly, I think you have an ICAT seed grant, or can you talk about the grant itself and the process there, or is that a Pinar question?
I think that, yeah.
So you want me to talk about how the ICAT grant enabled this work type of thing? Yeah. So we have an ICAT mini seed grant, and that actually really encouraged us to build an interdisciplinary team with Song, who we already collaborated with other agriculture and plant related projects. And then we were very inspired by this call, and we brainstorm about how we can, come up with a idea worthy of ICAT's, missions, and then we find out that if we, combined Song's expertise in plants and genomic sciences and our expertise in generative AI, that could be a very interesting combination. And we came up with this idea, and we really, in addition to, creating these visuals and then kind of increasing the awareness about climate change and kind of, increasing empathy towards this topic and making people more mindful about, especially computer scientists has to be, I think, mindful about the way they run, experiments or they train these models, because now this is a big, area of impact. So that was really very useful for us, and I also want to congratulate Connor, because he's working on this for the last 2 months. Because we got the ICAT grant a bit earlier, but I wasn't able to find a student who can work on it, since all my students were internationals, and then there was a bit of logistics there. But Connor recently switched his master to a PhD and working on this project, so I'm very grateful for the ICAT's support that enabled this great collaboration and this student working on this. Thank you.
Thank you so much. Thanks to the whole team, and thanks for sharing this. What a fun collaboration with plant sciences and computer science. That's what we do here. Thanks so much for being here this morning. I hope that your weekend is amazing. We'll be here again next week with more donuts and coffee, and I hope we'll see you there. Have a great day.